So we're going to take a look at this next section, and it's really similar to the last section in the sense that we're going to study quadratics. But in the last section, how are they written? In what form? What do we call that form? What was the term for it? What was it? Vertex form. So in the last section, we really looked at vertex form. In this section, we're going to really focus on standard form, and then we're going to kind of manipulate vertex form a little bit. Okay, we're going to move it over a little bit so we can change. So let's take a look at the second slide here. So standard form is the one that you've usually seen with quadratics. And we've seen this a lot this year. ax squared plus bx plus c. And this was our quadratic form that we also used for some of our work with other functions that look like quadratics that we can move them into. Now, this second line here says vertex form or completed square form. The reason it's called completed square form is because you use completing the square to come up with vertex form. I'll probably show that process today at some point if we have time. I'd like to do that. But anyhow, take a look at this. Take a look at this line right here, please. It's the same thing as what we did the other day. Except that k is no longer on this side, and k has been moved over to the right-hand side. All right, remember it was y minus k? F of x, this is really y, so this is really y equals. If I take that k and move it over, it would become y minus k. I need to blow my nose. Look at the first slide. Take a look at this first example for a second. So we're looking at an example here first that says determine the vertex and the axis of symmetry of the following function by transforming it into vertex form using completing the square. So we use completing the square on this in a moment. And then we're going to verify that the axis of symmetry is x equals h, but it could also be written as x equals negative b over 2a. All right, so we're going to verify that in this example. So let's go ahead and go through this process. So if I were to move things into complete the square form or try to complete the square on something, what was my first step in the past? What did we do when completing the square?
Did you move the 7?
Yeah, you always got the 7. So let's move the 7 over. Okay, so we move the 7 over to the left-hand side. And now it looks like we're starting to get into vertex form. We've got y, remember f of x is really y. We've got y minus k on this side. Oh, that looks nice, doesn't it? But I don't have a times x minus h squared over here. So on the right-hand side, we still have to complete the square. So if I wanted to complete the square for a problem like this, what should I possibly do to make life a little bit easier? George? Factor what?
3x.
Yeah, close. The x can come out, but I'm going to leave the x in. Just to factor the 3 out first. When I factor a 3 out, what am I left with?
X squared minus 4.
Minus 4.
Oh, minus 4.
X, yeah. The reason that it's useful to take a 3 out in this case is because now I can just complete the square within here. Remember how in the past we said divide by a? When you completed the square, you always would divide by 3 everywhere. And then this would become a 7/3. It was really messy. In this case, all we're going to do is factor 3 out and just use complete the square in here. But remember, if I put a number in here like plus 5 to complete the square, whatever it is, I'm really multiplying 3 by it, right? See the 3 that we took out? It's out here. So if I put a number inside, it's really not that number on both sides. It's 3 times that number. So if I were to just forget everything else and look at this and complete the square, what's half of b? Square that. So I have to add 4 in here, right? But remember, the 3's out here, so it's really 3 times 4. So what am I really adding to the right side? 12. Again, on the next line, I'm going to put a 4 in there. Okay, this 4 right here is what I'm adding to the right-hand side. So you would think, oh, add 4 to the left-hand side. But again, you're putting a 4 inside this parentheses, and there's a 3 on the outside. So inherently, you're adding 12 to both sides. All right, so those balance, believe it or not. By adding 4 to the right-hand side in the parentheses, because the 3 is on the outside, it's the same as adding a 12 on the left-hand side. So this is completing the square still, but it's a little bit trickier, because now you've got a y, you've got variables going on, and it looks like it's confusing, but it's not. It's going to simplify nicely. On the left-hand side, -7, +12 gives me +5. On the right-hand side, what is that quadratic if I write it as a square, George?
X minus 2.
Very good, George. X minus 2, that quantity squared, would give me this. And if you didn't know that, remember, completing the square, whatever half of b is, always shows up here. This is really good practice for completing the square. Whatever's half of b always shows up right here. So now I'm in vertex form. Does everybody see that it's in vertex form now? Here's f of x. What is f of x really? So it's really y minus k equals a times x minus h squared. Look at that. So what's the axis of symmetry here? What's the axis of symmetry on vertex?
2.
Just 2? You're just going to say the number 2? Give me more, Tristan.
It's 2 because you can see H.
But 2 is not a line. You can't just say 2.
It's up to
So it's, what's the equation?
uh,
What's the equation of any vertical line? Any vertical line.
oh, X.
Good, there you go. There's our axis of symmetry. X equals 2. It's really important to write x equals because the number 2 alone, what does that really mean, right? X equals 2 is a vertical line going through 2. So he's correct. And Tristan sees this because h is simply 2. So that means that the vertex must have a 2 for h right here. Remember, these, take a look, people. Write a note if you have to. These are always equal to each other. The x-coordinate of the vertex is always the axis of symmetry. Always, 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 always. Luke, what's the y value for the vertex?
Is it 5?
It's not 5, Luke. But you're close, Luke.
Is it
I said you're close. What do you think that means? Giving you a hint.
2, 5?
Close. Not 2, 5. You just recreated it. You're giving me the whole coordinate, which is good.
Is it -5?
It's -5 for the y value.
Oh, this minus 5.
Yeah, remember that, okay, guys? How do I get y minus k? Well, if this was a +5, remember you end up taking the opposite, because really it's like y minus -5 is what gives me y plus 5. So there's my vertex and axis of symmetry. The question, though, besides this says the following. Look up here, please. Look at this part. It says, verify that the axis of symmetry in vertex form could also be written as -b/2a. Well, what's a, b, and c from this original function? Oops. Go back to the original function, please. In the problem itself, in the word problem. What's a, what's b, what's c? Bridge?
A is 3, B is -12, and C is +7.
Do we all see that, a, b, and c? Where are they coming from? They're coming from the standard form in the problem. F of x equals 3x squared minus 12x plus 7. So, the question becomes this. I could also do the axis of symmetry this way. That's the statement. Can we prove that that's true? Well, just go ahead and do it. So this is our standard form on the right. We can use x equals -b/2a. That's what the axis of symmetry is in standard form. Negative b would be -12 over 2 times a. That'll give me +12 over 6. +12 over 6 is simply 2. So either way you do this, you get the same axis of symmetry either way.
So without doing that work, we're just able to convert it from that form to the formula form.
Yeah, so if I were doing this now from this point on, I would not convert to vertex form. That's a lot of work. See all this work we just have to do here? I would go right into using -b/2a, and that'll give you the axis of symmetry right off the bat. Again, write yourself a little note. When in standard form, use this formula. When you're in standard form, just use this formula. Anybody recognize this is where like it all ties together? It's all going to come together here. Anybody recognize where negative b over 2a comes from? Annie, got it right? Yeah, it's in the quadratic formula. Where is it, the quadratic formula? Negative b over 2a. Where is it, George?
It's the first thing. So
Yeah, it's when the discriminant equals.
0.
Yeah, think about the discriminant equaling 0. Do the quadratic formula in your head. X equals negative b plus or minus 0 all over 2a. Does the plus or minus 0 affect anything? So it would just be the negative b all over 2a, right? There it is. Write yourself a little note. This is just the beginning of the quadratic formula. That's all it is. Now, if I wanted the vertex and I wasn't in vertex form, so let's say, look, cross this. You don't have to do it. I'm going to cross this off. Make believe I didn't do any of this work at all. And I wanted to get the vertex. And I know that the axis of symmetry is 2. What could I do to get the vertex? So I know the axis of symmetry is x equals 2. And I didn't have any of this done. You cannot assume you have this done right now. Let's say we're just doing the right side. And I have the axis of symmetry, but I don't have the vertex. How do I find the vertex, Max?
Plug it in the standard form.
Why?
So that would be the initial.
For what?
That's okay.
Which is? So you plug into standard form to get the y-coordinate of the vertex, which is what you're missing. So recognize that, remember, the vertex is always whatever the axis of symmetry is, comma y. So the question is, what's the y value when the x value is 2? Because this will always be the same. I said that earlier. This 2 showed up here. So if I take a 2 and plug it into the original function, I'm simply saying, I'll put a little line here. I'm simply saying, or Max is simply saying, what's f of 2? So we take a 3x squared minus 12 times x plus 7, and that will give me negative 5. Again, run the axis of symmetry through the function, evaluate the function at the axis of symmetry to give you the y-coordinate of the vertex. Questions on this first one? So I don't know if on the next slide, let's see if I did. No, I didn't. So I wrote a generalization in my notes, and if this makes sense, feel free to write it. If not, you don't have to write it. The vertex, when in standard form, could be thought of as negative b over 2a, comma, f of negative b over 2a. That's what the vertex can be thought of as. What am I saying by this? If I'm writing notes and I'm a student, I would be like, oh, what the heck is he writing here, right? Well, what is this really just? The axis of symmetry. So what I'm saying is, if you ever want the vertex, just get the axis of symmetry in standard form, which is what we did, which was 2, plug that into the x coordinate right here. Then do what? Take the function and put what into it? The axis of symmetry into the function to get the y coordinate. That's what Max told us to do. He said, you know what? Let's take the 2 that was the axis of symmetry, plug it into the function itself. That's what this is saying to do right here. George, question? Good? Okay. I only asked because you had a look on your eyes that looked like you were like, good? Okay. All right, let's press on. So given the following, determine the vertex, the domain, the range, and the zeros. So let's go through a problem like this together first. Then we'll give you a little time on your own to do some others. So the vertex, right off the bat, what is this not in? Correct, that's true. So I could convert it, but I don't want it to do that, remember? It's also not in what?
Order.
It's not in order. And a lot of you made this mistake on the last quiz. I'm pointing this out. A, B, and C are not 3, 4, and negative 1 here. It's got to be in order. Okay, so it's really negative x squared plus 4x plus 3. That's how I have to write it. Remember, it's in decreasing order of the exponent. Decreasing order of the exponent. So in this case, A is negative 1, B is 4, and C is 3. A lot of mistakes on the quiz with this. A lot of them. More than like 1 or 2, like 5 or 6. Now, if I'm trying to find the vertex of this graph, can I find that right away? Can I find the vertex right off the bat anymore? No. because it's not in vertex form. I can't just identify the vertex anymore. So what do I start with then?
Standard form.
It's in standard form, so what do I start by finding? The what?
The vertex, or
The other one. Axis of.
axis of symmetry.
There you go. So let's find the axis of symmetry first. And remembering that the formula for that is negative b over 2a. You really don't have to memorize this formula because it's just the beginning of the quadratic formula. Forget the discriminant, and this is what the quadratic formula always becomes. Literally, cancel out the discriminant, you're always going to get this as the formula. So you don't have to rememorize this if you don't want to. Just remember it's the beginning of the quadratic. Negative b over 2a will give me simply 2. It's not always going to be 2. The last problem had 2 also. It's just a coincidence. So if that's the axis of symmetry, x equals 2, and I want the vertex, I know that I'm going to have a 2 already. Again, the axis of symmetry is x equals 2. That's got to be a 2. How do I find the y value again, Annette? The y value.
So you take that value and you put it into f of x, so f2.
Very good. So g in this case, but same thing. You plug it into the function itself, so we'll do g of 2 here. If I want to know what g of 2 is, I literally plug that in. Hey, something I want to point out. Everybody take a quick pause and look up. There's another common mistake I see all the time. Here's my function right here. Luke, look up. Come on. This symbol means the opposite of x squared. Let me make that clear again. Although you want to use the word negative, right? It's tempting to say negative, but then what you would do is some students do negative 2 and then they square it, which means what? But really, this is the opposite of 2 squared. So when you square this 2, this is really 4, but the negative actually carries down. Okay, so I'm going to end up getting 7 here for the coordinate. Again, it's very, very misleading because you see the negative here. And 9 out of 10 students, they seriously plug in a 2 and say, oh, negative 2 squared. It's not, though. It's the opposite of 2 squared. So your vertex is 2, 7. Again, the 2 coming from the axis of symmetry, the 7 coming from plugging the axis of symmetry into the actual function. You have a question? You have a look on your face, Max. Okay. Now, before I get to parts B and C, I want you to quickly draw me a sketch of what you think this looks like. Just a sketch. Just the sketch. Here's my vertex. I'm hoping yours looks something similar to that. Now, you have a calculator, but please don't use it right now. You don't need it. The A value in the standard form, the A value is also indicating whether it opens up or down. So in this problem, A is negative, isn't it? It's negative 1. So which way is the graph going to open?
Down.
It's going to open down. Just like vertex form. Write yourself a note if you have to. Okay, it's going to open down. Now, before I put it crossing the x-axis, we'll figure that out for part D, right? Part D will give us the zeros of the function. So I'm not going to cross the x-axis, I'm just going to draw my sketch like that for now. But I do want you to recognize here that the graph only opens down. It doesn't go up. So there's some limitation. Is the limitation to the domain or to the range? What do you got? The range. So first of all, I'm getting really scary looks right now. Let's define range and domain for everybody in case there's some of us that are forgetting what they mean. Range and domain. What do they actually mean? Luke?
Isn't domain all the possible values of x and range is all the possible values of y?
So why did Kate say that the range is limited?
Because it doesn't go above 6.
Seven, right? Look at it's right there.
It's on the 6.
It doesn't go above 7 in this problem. Everything for this function starts up here. Take a look. It's 7 and goes down, right? So the range would be what? I'm skipping to part C. I know that. The range, we have the domain here, and then we'll do the range. What would the range be then? If it starts at 7, but it's everything below 7. It includes 7 also.
Less than or equal to 7.
Good. Okay, there's your range right there. Part B, the domain. What is the domain of this and all quadratic functions? All quadratic functions. From where to where? Yeah, you can't just say infinity though, Max.
All real numbers.
All real numbers. From negative infinity to infinity, or all real numbers. So here's our set notation we're writing. I'll put the interval notation in blue. In blue, you could have written it like this. And in this one, you could have written it as... So in blue, I'm putting interval notation. You don't have to use interval notation, but you really need to be familiar with it. So all real numbers means not infinity, but from negative infinity to infinity. And anything less than or equal to 7 means from negative infinity up to 7, including 7. Okay, including 7. How about part D? How do I approach part D? Find the zeros of the function.
Put f of x is f of 0 in there. No.
That's finding the y-intercept.
Oh.
When you set x to 0, you do f of 0, right? And you get the y-intercept. You're on the right track, though.
Do you set g of x equal to 0?
Set the whole function equal to 0. Don't plug 0 in for x, okay? Like g of 0 means you're plugging 0 in for x. Here we want to set the function itself equal to 0. And then solve for x. How do I solve this for x? What's the easy way? George, what would you recommend I do? You can complete the square or the quadratic formula. Yeah, for sure, both. But do I have to complete the square here, I guess? Yeah, I do. It's not factorable. But what would I maybe start to do first? It makes life easier on me. You don't have to do this, but it might be useful.
Divide by negative.
Yeah, when everything's equal to 0, you can divide by -1 very easily. Even though this is not the same function as the one above, it'll have the same intercepts. What do you notice, by the way? Everybody pause for a second. This is where you really, let's see who knows what they're doing. What's the difference in these two graphs? If I were to have them both equal to y, how are they different? Bridge.
They open up, one opens up and one opens down.
Very good. But they have the exact same what?
Vertex,
No, believe it or not. The vertex would be different, actually.
axis of symmetry.
Correct. Axis symmetry. What else?
Like intercepts.
Yeah. So if the x-intercepts are here, visualize, please, okay? Here's the graph. Here's your x-intercepts. It would literally be like this. Same x-intercepts, except flipped up. So by dividing by -1, I'm still going to get the same x-intercepts. And part D says find the zeros. The zeros of the function are the x-intercepts. So by dividing by -1, I'm still going to get the same x-intercepts for a different function. But I have what my function looks like already on the top right. So I can divide by -1 and get the x-intercepts. The reasoning is because now it can maybe be factorable. It's easy to look at this way. Turns out it's not factorable. So George was making a good point. He said use completing the square. Either way, I'm going to use the quadratic formula. X equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a. Under the radical, I'll end up with 7 under there. Right? It'll be 16. What would it be? It'll be... Oh, because I'm going to simplify. That's why. I'll end up with 28 under there. And then simplify it further. So it's going to be 4 plus or minus root 28 over 2. But root 28 is really 7 times 4. Which will give me that answer. Which will result in... Take a look at the math behind it, please. Make sure you get the same answer. When you have root 28, think of this as 4 times 7. 4 comes out front as a 2. These are all divisible by 2. So this becomes a 2. This becomes a 1. This becomes a 1. You don't really need it. Now, is it useful when I'm graphing to have those numbers there? Is that going to help me identify where they are on the graph? 2 plus or minus root 7? Probably not, but I do want to point something out. This is, again, I keep saying everything is going to come together in this lesson. This is huge, this next part. Huge. 2 plus or minus root 7. Explain the significance. Think about that tonight. Tomorrow I'm going to lead off with this question. That'll give you time for the project. You don't have homework tonight because we're going to finish this lesson in class later this week. Think about it tonight. Seriously, here's your question. Explain the significance of this right here. Let's see if we can physically on the graph what the significance of this is. We're now on day 2 of this lesson. I posed a question at the very end that said, explain the significance of this answer. Has anybody actually thought about it or figured it out? Hannah?
I thought about it.
Uh-huh.
It's the same as the vertex, but that's
It's close to the vertex, Hannah. The vertex is 2, 7.
yeah.
This is 2 plus root 7, 2 minus root 7. The 7 happens to be a coincidence, by the way. The 2, though, is not. Is my hint. The 2 is not a coincidence. What do you got?
The 2 is like middle point, kind of, because it's like an equal amount from each side if it's like negative and positive.
That's exactly right. Very good. So let's talk about this. Let's draw this. So let's go ahead and draw a graph with the vertex at 1, 2, and up 7. 1, 2, 3, 4, 5, 6. I put 8, but we'll go to 7 right there. We put our axis of symmetry right down the middle. Now, remember the quadratic formula. Negative b plus or minus whatever all over?
2a.
So negative b over 2a, isn't that just 2? Think about the quadratic formula. This is the beginning of the quadratic formula. This is negative b over 2a. That gives you the 2. Root 28 over 2 gives you the root 7 here, really. Right? This part is here, and this part comes from here. So in reality, Kate is exactly right. This is like a midline. And this is like what we call, remember the deviation? Who remembers that from the number line? Remember the number line? You found your starting point, and then we had deviation, left and right. We shaded the region in the middle, all that stuff. That's exactly what this is. The roots, do me a favor real quick on a calculator. What's 2 plus root 7 going to give me? I know it's going to be more than 4. What's going to be, give me a decimal to the nearest 10th. 2 plus root 7, and then, 2 minus root 7. Give me both of those.
2 plus is 4.645 versus 2 minus 4 point. Okay.
To the nearest 10th.
It's 6.5.
So the nearest 10th would be 4.6. What's the nearest net 10th in the next one?
And negative
Good?
negative 0.6.
Okay. So take a look at my values right here. 4.6, negative 0.6. How far is 4.6 from 2? Well, it's root 7 away. So if I go over to 4, so this was 2, 3, 4, 5. 4.6 is right there. Negative 0.6 is right here. Well, if you look at this, follow the cursor, please. 1 unit, 2 units, another like half. 1 unit, 2 units, like another half. Well, this distance from here to here is root 7. This distance is root 7. How do I know it's root 7? Because my roots are root 7 away from 2. Again, 2 is my axis of symmetry. It's like the starting point. And then I deviate root 7 this way and root 7 this way, giving me my 2 intercepts. Okay, and there's my graph. Any questions on this one? Can we continue? So the root 7 here, I want you to understand the significance of your answers. The root 7 is like a deviation, and the 2 is like a starting point. It all comes from the quadratic formula. Right? This is your starting point right here. Negative b over 2a. That's your starting point. This is your deviation. In blue, root b squared minus 4ac all over 2a. This is your deviation, really. And this over here is like your starting point. So the reason that you're taught to solve linear inequalities that way, with starting point and deviation, that graphical approach we called it, because it really actually plays a role later on. This is where it comes into account. Okay, again, how far are these roots? They're equidistant from the axis of symmetry, hence symmetry. That's why the word symmetry is used, because you have symmetry. Each root is the same distance away from this axis of symmetry. All right, next, we want to talk for a little while about intercepts. And if you recall, I spoke about this already in the last set of notes, in 7.5. And do you recall this diagram? Does this ring a bell? You saw this diagram in 7.5, provided you watched the rest of the notes. And we talked in general in that section with vertex form. But here, let's talk about specifically the discriminant. Again, when the discriminant is positive, how many roots do we get? This could be everybody answering, you don't have to raise your hand. When the discriminant is 0, when the discriminant is negative, how many real roots do we get? No real roots, okay? So on our graph, we can physically see this occurring. I'm going to go to a question on that in a little bit, but that's all I want to get to for this part for now. Okay, for now. And in general, I should mention this. We're just talking about intercepts. When you want to find the x-intercept, what's the general rule? Set y equal to 0. When you want to find the y-intercept, set x equal to 0. So for a quadratic, can we come up with a generalization here? What's the y-intercept for this? Quick, come on, you should be done. What's the y-intercept? Thank you, George. Why? What do you do? Set. Yeah, set x equal to 0. This drops off, this drops off. There's your y-intercept. So write yourself a note, please. The c value in standard quadratic form is the y-intercept. The c value in standard quadratic form will always be your y-intercept. Okay? Always be your y-intercept. Can I press on? We're good? All right. So this next part we've already talked about. See how much everything's coming together? We've talked about all these things, but now we're applying them. We're going to see in the next section, actually, we're going to talk even further or more about this kind of stuff. Well, right now, let's simply talk about A being positive or negative. These are called extrema. Extrema. What does extrema come from? What word? Extreme. An extreme can be either really high or really low. Those are extremes. An extreme is really like a range of values. So if I want to think about when will I have the minimum in a graph, well, just look at the figure here, please. When A is greater than 0 or when A is positive, the graph opens up. If the graph opens up, there's a valley or there's a minimum there. In science, you might call this a trough. Trough and minimum are the same word. In science, you might call a maximum a crest. Okay, in science, you've heard the words crest and trough, which just means max and min. So in these problems, I want you to recognize that when A is greater than 0, the graph is going to open up. When the graph opens up, you have a min. When A is less than 0, the graph opens down. Therefore, you have a max. Now, vocabulary. This is something that affects all of you, even those that are really the strongest in the class. Because vocabulary is something that it's not really just straight math. You have to know your words. So, if I ask you to find the maximum value on a graph, the maximum value versus finding the coordinate of the max, how do those things differ? If I said to you, look at the graph on the right here, please. Use this graph. Assume the intervals are ones. Okay? Assume you're going by ones everywhere. If I ask you, what is the coordinate of the max versus what is the maximum value? How do your answers differ?
Maximum value is y.
Very good. Very good. That's exactly right. So let's give this a coordinate here. This coordinate will be -1, 4. So for this graph, the max value is equal to 4. Value refers to the y value. Look at the little asterisk I have here, this little note. The value of the extremum is the y-coordinate of the vertex, and the location of the extremum is the x-coordinate. So the location that the max value occurs is simply -1. We're all focused, I hope, because this is a problem that I'm telling you on every test. At least 1 or 2 of you are going to get this wrong. And I'm not trying to be mean, I'm being honest. Every year this happens. Prove me wrong, please. Listen carefully and prove me wrong. I'm telling you the past. The max value of this graph is 4. Where does it occur? It occurs at -1. Write yourself a note. The x-coordinate is more of a location in math. The independent or the horizontal axis is like your location. The vertical axis, the height or the value of the function. Yes? Okay. The actual coordinate, though, of the max is -1, 4. All right, let's jump right into an example now. Now that we've done a little bit of theory here, let's jump into example. Determine the maximum or minimum value of the following and determine its location. Are you going to find the value or the location first? Hannah, value or location first? How do you find the value? That's the y-intercept. It's not necessarily, right? A graph would do this, right? Cross the y-axis, still go up, right? All right, good. So Hannah makes a great point. Find the vertex, really. But to find the vertex, you first need to find the... So really, you find the location first. Okay, so in this kind of a problem here, you want to think about the fact that it's very tempting to try to find the value first. And remember that really what you need to figure out is the vertex. This is the location. This is the value. That's what we're looking for. So Hannah's absolutely right. You want the vertex. I would not choose to put this into vertex form and rearrange it. It's messy. It's a lot of work. I would find the location first by remembering that the vertex or the max or min always occurs at the axis of symmetry. So let's find the axis of symmetry with -b/2a. So I know already that the location is -1. That is where the max or min will occur. Max, what do you think it will be here? A max or a min? Yes, you do. Sure you do.
Minimum.
Why? Come on, go to the last slide. You know this. Go to the last slide next. You should be able to answer this. Give it this. On the previous slide, we talked about whether something is a max or a min.
So it's the maximum value.
I read it the first time. It's a min. Look at the a value, Max. The a value is positive or negative in this case.
Positive.
So the graph opens which way?
Oh, okay, I see.
Now you see it?
Yeah.
All right. So if anyone else doesn't see it, take a look up. This is what I'm talking about. The graph opens up. So what does it have? A bottom. If it opens down, it has a top. So this graph will certainly have a minimum. That's why it says min or max there. Okay, it's going to be a minimum value. Now the question is, what is that value? Well, I know that I need to figure out what the vertex is. I've got -1 right here, but the question is, what goes in for the value? How do I find the y-coordinate anytime in math, ever, if I have the x? How do I find the y? Just plug it in. Plug it in. All right, take that -1, plug it into the function. Let's do f of -1. So literally plug in the axis of symmetry, meaning the location of the min or max, plug that into the function to find the value of the min or max. What does that value turn out to be? Okay?
Like the coordinate,
Now just give me the value for now.
-5.
Very good. And that's going to go up here for my coordinate. So the value of the minimum of this function is -5. It occurs at x equals -1. So if I wanted to draw a graph of this, here's my vertex at the bottom. I go down 5, over left 1, and then I know the graph is going to open up. I don't know where it's going to cross the x-axis, so I'm not going to show it crossing for now. See what I'm saying? Unless I knew the roots, which I can find. But right now, I just probably didn't find the roots. So I'm just going to draw the graph, not even crossing the x-axis yet. We know because it's an arrow, though, what's it going to do? When there's an arrow, it continues. Good. Okay, it's going to continue moving. So it will cross the x-axis, but I'm not going to show where because I don't know where it is yet. Questions on this problem? Hey, what's the range of this function?
-5.
Or more. Or more. So y, the range is y greater than or equal to -5. What's the domain? What's the phrase we use though? All real numbers. Yeah, from negative infinity to infinity. You can't just say infinity. Okay? From negative infinity all the way to infinity is the domain. It goes on forever. All real numbers. Remember, guys, the range is the thing that is limited. What is the range limited by? The range will always be limited by what?
The vertex.
Very good. The vertex. What specifically about the vertex? It's
Value,
which one?
the maximum.
Good. The max or the min value. The y-coordinate is going to be the thing that limits the range because this is the range based on y. Okay? So if I have a function like this, it's going to be y less than or equal to whatever the max is for the range. If I have a function like this, it's y is greater than or equal to whatever the min is. So when you have a min, you're going to see greater than or equal to. When you have a max, you're going to see less than or equal to. Okay? Min versus max. Questions? All right, good. Example 4, let's take a look. We've got a function here written in standard form. We're given the y-intercept in 2 points. And the question is, determine the values of a, b, and c. Determine the values of a, b, and c. That's not explicitly written, right? But how do I know that that's the question being asked? It says, find a function in that form. What do you think I could do to start this? What do you think, Annette?
Well, C probably equals 7, so you have C already.
Everybody see that?
Yeah.
I know. This is so much fun today. C is absolutely 7. Very good point. Annette remembered, hey, the y-intercept comes from C always. So right off the bat, start with that. Bridge, what do you think we can do with these 2 points?
Plug them, or do y1 minus y over x1 minus that.
That would give me a slope, but this is a quadratic. Start with what you're going to say in the beginning.
You plug them in.
Plug them in, literally.
You plug in.
Guys, whenever you're given points and you don't know what to do with them, plug them in and see what you can get. So let's plug in the first one, 310. Where does the 10 go?
Into the y. So
Good.
10 equals,
Good, keep going.
10 equals 3x squared.
Uh-uh.
Or a times 3 squared.
Good.
Plus b times 3, or 3, and plus 7.
Very good. How many variables are unknown, unfortunately, Tristan?
2.
So what do we need?
System.
So we need a second equation. Where do you think we're going to get that, Tristan?
The other.
Do you see how it's like kind of leading you in there? You're given 2 coordinates, you got to use them. So you're going to use the second coordinate now to come up with a second equation. Now, it's very tempting to solve this by hand. Please don't. Go to a matrix. It's a waste of your time to do it by hand this part of the year. Okay? Use a matrix. There's no error. You're going to be quick with it anyway. So here's my matrix if I write all my numbers out. I'm going to move the 7s over. Everybody agree with that statement? Move the 7s over. Okay, those are done. I move both those over. 3 squared times a is going to be 9a plus 3b. The second line, negative 2 squared is really 4, and that's going to be minus 2b. So I'm going to evaluate these squares to give them coefficients. Now, when we did this earlier in the year, if you recall, we wrote our matrices where we had it written like this. Okay, that's how we had it written with the matrix. It's always your coefficient matrix and your constant vector on the right. So let's do it continuously like this. So let's continue that pattern. So our matrix is really 9, 3, 3, 4, negative 2, 18. Who remembers what the command is in the calculator?
Is it REF?
RREF. Okay, very good. RREF. Yeah, the second R, someone below. So once you've typed your matrix in, 9, 3, 3, 4, negative 2, 18, quit out of the matrix. Go press second, RREF. Enter matrix, whatever you put in, matrix A or B or C, whatever it is, and come up with your result. If you don't know what I'm saying right now, you need to advocate. That means one of 3 things. Go to Moodle. Watch the video I put up on how to use a matrix in the calculator. Option 2, ask me about how to do it. Option 3, go to YouTube. Type in matrix on a TI-83, TI-84, whatever. Okay, you got to know how to do this stuff. The resultant will become the following. Check yours, please. Don't assume I'm always right. I'm not. That's my resultant. It's not showing up. Give it a sec. Airplay's off.
Yeah.
There it is. There's the resultant matrix. Please remember what the first column was. The first column was A. The second column was B. First column was A. The second column was B. So this really says 1A equals 2. This here says 1B equals negative 5. So A is 2 and B is negative 5. So my final answer for this whole long problem is going to be f of x equals ax squared plus bx plus c. Okay, there's my answer for this problem. What's important here is not practicing the matrix. If you have trouble with that, that's okay, but you need to get better at it. What's really important here is looking and identifying that, you know what? We're given 3 things. Because what we were trying to find in the beginning, 3 values, A, B, and C.
How do we get to R?
You use the 7 as the y-intercept right off the bat, which means you only have to look for A and B, right? So there are only 2 unknowns, so we use the other 2 coordinates to come up with A and B. Second matrix, over to edit, over to math. Yeah, the RREF. And then go back to the matrix. Which one was it, B? Yep. 2 more questions for today. These are going to get even trickier. You need to be making sure you're focused right now. The next 2 are going to get a little bit tougher. Make up your own quadratic function. Everybody on your own do this, and then check with your partner next to you, or do it on your own completely. Make up your own for the following sketch and discuss why you chose those values. Think about everything we've talked about. This is a hard question. It's not easy. There are a multitude of answers to be right here, but think about where A is involved. Where is B involved? Where is C involved? Okay, think about physically where they're involved. Try to come up with a function that works for this. I'm not giving you any numbers, but you do know that both roots will be negative. You know that the axis of symmetry will be negative. You know that the vertex will be a max, not a min. So you know stuff already. Characterize what you know based on what you see. If I see a graph that opens down, I might think, oh, right away, something. So that's what you have to start thinking about. Write down all those characteristics before you come up with your function. Based on the graph, write down what you know. I want to see those parameters. I don't want to see an answer, please. I want to see parameters first. Because it opens down, blank. Because this is here, blank. Because there's 2 real roots, blank. You should have 4 statements to be made. 4 statements. Give me one of them, Tristan.
C has to be negative.
C has to be negative. Very good. Right away, C's got to be negative because the y-intercept in this case is negative. Again, the y-intercept, if I continue this graph, here's your y-intercept, it's negative. Therefore, this graph, or this function, must have a C value that's negative. I agree. Next. Next parameter. George.
It has to be less than 0
Why?
because it opens down. So
Good. Okay, I'm giving reasoning next to each thing. It's going to catch up. Airplay is like really off the. And again, A is less than 0 because it opens down. C is less than 0 because it's a negative y-intercept. They're there. They'll appear in a minute. I promise. I hope. Third criteria. Max, go for it.
B has to be a lot bigger than C.
Where are you getting that from?
And A. Because like the discriminant.
All right, so give me not just about B, give me about the discriminant. The discriminant must be good. So let's write that down. Because there's 2 real roots. It's catching up, I promise. So let's jot down the following. I have it on mine already. B squared minus 4ac greater than 0. That's the third criteria. Because there are 2 real roots on this graph. I'm going to pause, guys. Fourth criteria is the toughest by far. Can anybody figure out the fourth criteria? Yeah? What do you think?
The B has to be less than 0.
Why?
Because the symmetry is equal to B over negative 2A. It's less than 0.
This is equal to negative b over 2a. Everybody sees that? Yes? Now, what was the first or second statement we made? We said that a was what? Negative. If a is negative and there's already a negative, what's going to happen to those 2 negatives there? So what must b have to be then? It's got to be negative because the actual axis is on the negative side. If this axis were over here, then you can make b positive because the negative a and the negative in the front up there would cancel. But again, because a is negative and there's already a negative sign, this being negative right here is going to drop off with this one. Those negatives cancel. So b itself must also be negative. All right, all those things stated, we still don't have numbers, right? We don't. But Max made a good point. Max, talk about that point again, Max.
The B has to be bigger than C.
B has to be bigger than C.
Well, less than the opposite of
Okay, give me more. Help him out. There's more to it than just C, obviously. Because look what else is involved here, right?
A.
And A. So you recognize that what? Pick a value for A and C.
B squared has to be greater than negative 4ac.
Then positive 4AC. Because you're going to move it over, right? So what happens here is this. Pick a value for A and C. Those are the easy ones. Give me a value that are negative for A and C. It really doesn't matter actually here at all. And? Okay. So A is negative 3 and C is negative 5. Fine. That works. Now if I take 4 times A times C, what do I get? 4 times 3 is 12. 12 times 5 is 60. It's going to be negative, negative, negative. So I'm going to have B squared. I'm going to have B squared minus 60. So what must B be? What must B be? Its square must be.
Oh, its square must be
Good. B squared must be more than 60. If B squared is less than 60, I'm going to have something like 40 minus 60. Isn't that negative? And a negative discriminant would tell me there'd be no roots. And you can see there's 2 real x-intercepts here. Because there's 2 x-intercepts, this has to be positive. So what's the value for B that you could use? What's the value for B that when I square it, it's more than 60? Give me a perfect square, no?
8.
8. But because B has to be negative,
Negative 8.
negative 8. There's a graph that would work. Okay? So again, A, B, and C are absolutely all negative based on some parameters, but when we square -8, that becomes positive 64 minus 60. Do me a favor, please. Go ahead and graph this. Get your calculator out. Go ahead and graph what we just came up with. Go ahead and graph that, please. Take a look at it. Make sure it verifies what we just said. Hey, you might not see it on the graph, so you might have to zoom out a little bit or something, but actually I think you will see this. Yeah, you'll see it. What do you got? Show me.
This tiny little graph.
Yeah, good, good. What do you got?
Oh,
Like this?
yeah, almost.
It almost looks like there's only one root, right? But if you look at it closely, you'll see that there's two x-intercepts, actually. It almost looks like this is tangent to the x-axis. When it touches, it comes back, but it actually goes through the x-axis. Next.
Isn't that like all parabolas are exactly the same?
What?
They're all the same shape, right?
Yeah. They're all the same
Like
shape.
different, like zoom in or out.
Correct. They're different locations, and they're also different widths. Remember we talked about how like the A value tells you if it's wider or narrower and stuff?
I know, but doesn't it always get infinitely wider, so they're all the same?
In a big scheme of things, if you zoom out enough, all parabolas really do look the same. Yep. And if you change your window settings, you can make two graphs with totally different equations look identical on a calculator if you just go by different numbers. Right? Keep that in mind too. Hey, what you should be seeing, honestly, is something like what we saw to start. Now, just so you know, if we use the exact graph, it looked like this. Okay, that's what you should be seeing in black there. But there are two x-intercepts. Why are they very close to being one x-intercept? Let's see if anybody gets that part. This is if we really know about math. Why are these x-intercepts so close to being almost at the same point when there would only be one x-intercept? When do we have one x-intercept? When the discriminant is 0, remember? It touches the x-axis, and then what does it do? It comes back. It doesn't cross, right? Look at our discriminant. What do we get? 64 minus 60. Pretty darn close, isn't it? Our discriminant is really close to 0 in this case. So if you had jacked up the value of b to like -9 or -10, that would have made the graph slide up a little bit and expand a little bit also. Do you see what I'm saying?
Yeah.
Okay, there's a lot happening here, guys. There's a lot. That's why I wasn't joking about this section being a long section with a lot of theory. It all comes together here. Everything we've learned all year about quadratics, about the discriminant, about roots, everything is all coming together. We got one more difficult question today. Part A, do on your own. Part A, do on your own. And at this point in life, or at this point in math, you should be able to do part A on your own. Part B and C is a challenge, so if you want to try that, go ahead. I'll give you like a minute for part A. What's good for part A? What'd you get? Come on, A is so easy, guys. You don't have to actually graph this. No, what's the answer? Part A, let's go. What is it? Why is it twice? The discriminant, guys, look at the discriminant. Remember, the discriminant tells you how many real roots or how many times it crosses the x-axis. Please don't actually calculate anything right now besides the discriminant. That's all you need. Ash, what did you get for your discriminant for part A? Yeah, that's true. She sees A and C are different signs, so it's going to be something plus something, right? Under the radical? Absolutely right. So your discriminant is going to be some positive number. It really doesn't matter Everybody see what Ashley did there? Let me show you what she's doing. Look. Look up, please. Look up. Don't even look at the values of the numbers. Just look at the signs. See how this is opposite signs? Whenever A and C are opposite signs, this is always going to work nicely, because if these are opposite signs, this makes this whole thing a negative. Negative makes it a positive. So you get a squared value plus something. It's got to be positive. So write yourself a little note. That's a great thing to write down. When A and C are opposite signs, you're always going to have real roots. When A and C are opposite signs, you will always have real roots, provided all of your coefficients are real. It'd be a little bit weird, but if B were imaginary, it'd be different. How about part B? Can somebody quickly, not it doesn't have to be quickly, but could somebody tell me how they would approach part B differently than part A? Annette.
Well, I try to find the minimum or maximum, so that way I know where the vertex is, so I can see if it's, so say the vertex is like 1, 6. Well, since A is negative, that's gonna be a maximum. So I'm gonna know that if it's 1, 6, that means that the max is 6 for Y. So it can't intersect 7, it can't intersect 10.
That's a great way of thinking. I didn't even think about that. It's a longer way, but it works. There's a shorter way to do it, but that absolutely works. What she's saying is like, find your max or min, and then think about the visualization of the graph. We know that this graph, y equals 7. Well, where is that? That's right here. So Annette was saying, if your vertex is 1, 6, and because A is negative, it opens down, well, as a result, it's going to have no intersections with the line y equals 7. That's a great way of putting it. There's an easier, shorter way to do it. A shorter way, okay? Yeah, just plug 7 in for y. What did we plug in for y earlier for part A? We plugged in 0 for y, right? Because what's the x-axis? What's the equation of the x-axis? Y equals 0. Think for a second, please. This is y equals 7. This is, ready? This is y equals 3. This is y equals 2. This is y equals 1. What's the x-axis? Y equals 0, really. So we really just plug that in there. So in reality, what we're doing is we're saying, when is this parabola, when is this function going to get up to a height of 7? Well, let's take the function itself and set it equal to 7 to see when it's going to cross that. So in this second part, we could also just put a 7 here and then move the 7 over and get the discriminant again. Again, if I want to know when it will cross or be equal to a certain y value, set it equal to that y value. This right here, if you want to write yourself a note, this is, in English, this is saying the following. This is saying the function itself is equal to a height of 7. And that's what we're trying to figure out, determine how many times the parabola will intersect the line y equals 7. So is it going to do this? Is it going to touch once? Is it going to touch 0 times? What's going to happen? So what do we do here? We get the discriminant. What's the discriminant in this case? Very good. The discriminant is 0. What does that mean? Good. That means that if the discriminant is 0, there's going to be one intersection, right? Because when the discriminant is positive, there are how many intersections? 2. When the discriminant is negative, there are no intersections. Well, now, this graph would intersect once with this line right here. So maybe it looks something like, let's see, negative b over 2a would give that positive over negative. So it would be on the left-hand side. So maybe it's something like this. And it'd be actually a positive 4 as a y-intercept. So it's going to be like, let me do it better. That's what like the graph is going to look like here. Think about your original graph. The y-intercept was 4. That's right there. The axis symmetry is negative 6 over 2a. That would be some negative number. I know the line y equals 7 is the horizontal. So when it touches once, we get a discriminant of 0. How do you think we're going to approach part C? What's the answer?
0.
Why? The discriminant is not 0, 0 intersection, right? Because
It's the highest point is 7.
it's already at 7, which is the highest point. Look at the graph right here. Look at the graph drawn in black here. It reached the height of 7. So the third part says, when is it going to intersect, or how many times would it intersect the line y equals 10? That's right there. There's the line y equals 10. This was the line y equals 7. If it intersects the line y equals 7 once, right here, and opens down, does it ever intersect the line y equals 10? No. But can we prove this mathematically? Yeah, we can. We could say to ourselves, all right, take our function, the beginning, and set it equal to 10. And see how many real roots we get. See how many real roots we get. Move the 10 over. Find the discriminant. (36) minus, we're going to have 12 times 6 is 72, so negative 36. So the discriminant is negative, therefore there's going to be no intersections. With what though? No intersections with the line y equals 10. Y equals 10. Okay? This is the last part of 7.6. We're going to press on to 7.7 now at this point. Any questions on 7.6 you want to ask? The first part, let me reiterate, we set equal to 0 because we were looking to see when it's going to cross the x-axis, and the x-axis is a height of y equals 0. So it's saying when is it going to intersect? Then we were asked when is it going to intersect the line y equals 7. So we set it equal to 7. I didn't realize the time was flying that fast. We set it equal to 7 and then 10. Hey, for those that may have struggled a little bit on this, try to slow it down for yourself. Maybe over the weekend, watch these last 2 examples again in the video, and make sure to press on to this homework over the weekend. We will do 7.7 Monday. We will have a quiz. I think the Monday quiz will mainly be 7.5 in the beginning of 7.6. Will probably not be the last things we just did. Okay? So 7.5 in the beginning of 7.6, and then problem set is due on Tuesday. Projects due Monday. I'm hoping you're done already with the project, guys.
I just have a question for the problem test on 7.5. So how would you solve that? Because like when you plug the numbers in, like in the example, it like